Hi everybody. So today we have with us Daniela Hadasch from Tokyo, and she will have a very nice talk about binaries in very high energy. And she got her diploma in 2008 in the Technical University of Dortmund in Germany. And at that time she was working on MAGIC, the MAGIC telescopes, and on binaries. I know for her diploma she was working on MAGIC, but on a special flare of a source, studying the high zenith performance of MAGIC. Then after that, she fell in love with binaries, and she started to work with them in very high energy and in high energy gamma rays as well. So she finished her PhD in 2013 in Barcelona, and after that she had a postdoc in Austria, and then it was in Austria, right? Okay, yeah. Again on very high energy gamma rays, and after that, from 2014, she's working in Tokyo now. And her favorite topic, the topic she's working on mainly, are binaries in very high energy. And this is a very important topic for people in very high energy, also because a binary that she will talk about soon was discovered by MAGIC, and so she will tell you also the story of this very important source. So, welcome, Daniela. Thank you so much.
Okay, hello everybody. Yeah, thank you very much for the opportunity that I can talk here in this very cute little cinema somehow. Yeah, my name is Daniela Hadasch, and I will talk now for almost 1 hour about binary systems at high energies. So there are several binary systems that are detected above 100 MeV. There we have the so-called gamma ray binaries, we have the microquasars, we have the novae, we have colliding wind binaries, and millisecond pulsars. So this is already a bunch. I don't have that much time. So I will focus just on these two classes, on the gamma ray binaries and on the microquasars. So let me first explain you what are gamma ray binaries. So actually there is no definite definition of it. What is common for them, they all show orbital variability, and one of the definition is that their gamma ray emission above 100 MeV is dominated. So here you see the spectral energy distribution of one of these sources, where we have the energy and the flux, and you see that most of the energy is emitted at high and very high energies. So this is the definition of gamma ray binaries, although we have some exceptions. For example, the Cygnus X-1, where the bunch of emission is actually emitted in X-rays. So it is a very vague definition. So the gamma ray binaries we know, they are all nicely distributed along the galactic plane. So this is an image seen in the GeV. There we have the Fermi satellite, which is observing the sky all the time. And this is kind of a picture of our universe seen in GeVs. So along the galactic plane, you have a lot of diffuse emission background for us. And there on top of it, we have several gamma ray binaries I want to present you today. So actually, we know something about them, but there is a lot we don't know about them. For example, what is the nature of the systems? So there are several models. We have, let's see, two big theories what they can be. They can be a pulsar with a BE star or a so-called microquasar. Well, and we have a pulsar with a massive star, but it's very similar to the first scenario. So a pulsar with a BE star means that we have a BE star with an decretion disk orbited by a neutron star. In the case of a microquasar, we have also a massive star, but without any disk, orbited by a black hole. So as I said, for most of them, we don't know the nature of the compact object. So we don't know if it's a pulsar or a black hole. Just for 2-3 systems, for this one, PSR B1259, we know for sure that we have a pulsar because we see pulsations. And for these two systems, Cygnus X-3 and Cygnus X-1, we are pretty sure that they are black holes. But for all the others, they could be either or. Okay, the energy range I want to present the binaries in is at, as I said, at high and at very high energies. So here you have the whole electromagnetic spectrum from radio over optical. Here we have high energy, very high energies. And as most of you know, I think it's that, well, most of these electromagnetic spectrum we cannot observe directly from Earth, just radio and a small window here in the optical. So in the energy range I want to present, we need the help of satellites and of Cherenkov telescopes, which use a special technique that we can detect these very high energy gamma rays in an indirect way. So the instruments that we are using to detect the sources at these energy ranges are the two satellites, the Agile satellite and the Large Area Telescope, the Fermi satellite. And we have the Cherenkov telescopes. There are 3 big experiments around the world, so for sure you know the MAGICs, here the neighbor island on La Palma. We have the HESS experiment in Namibia in the southern hemisphere, and we have the Veritas experiment in Arizona. So now let's start with the sources. The first source I want to present is LS5039, and here I want to take the opportunity to explain you very shortly what is the difficulty if we have high energy data, so data from the Fermi-LAT satellite, for example. So here you see a count map of the region where our source of interest is located. Here you have the galactic plane, and nearby you have a pulsar. So if you want to get this source, what you have to do is you have to subtract first this diffuse emission and the nearby pulsar. So when you do this, you remain with a very nice excess. I mean, this sounds very easy, but actually modeling or knowing this diffuse emission is very tricky and difficult and very important for the analysis of sources along the galactic plane. Okay, but for this source, so we subtract all this, we have a nice signal here. And in very high energy, it is actually a very interesting source because it is a quite stable source along the orbit. So let me just introduce it here very quickly. So this is a sketch of the source. Here you have the star, the massive star, orbited by a compact object. And then we have characteristic points along the orbit. So we have the inferior and the superior conjunction. This is when the compact object is in front or behind the star with respect to the observer. So the observer is somewhere here, down there. Then we have the periastron and the apastron. This is when both objects are closest or farthest away to each other. Okay, so now this compact object is orbiting the star, and what we see at very high energies, so above 100 GeV, is the following. So here we have the flux over the phase. So the phase, it goes from normally from 0 to 1. So we take all the data and fold it with the period of, in this case, of 3.9 days. So we know that this binary system has a period of 3.9 days. It means that the compact object needs this time to make one round. Yeah, and what you get then is this kind of sinusoidal modulation, where we have a maximum at inferior conjunction at very high energies and the minimum shortly after superior conjunction, so at this point. If we go now to high energies, this looks a little bit different. So, oops, sorry. There we have, here again, this is the light curve I showed you before with the maximum here, the minimum here. And in GeV, it looks the opposite. So we have the minimum when the star is in front, when the compact object is in front of the star, and the maximum when it's behind the star. This can be explained by the idea how we think that this emission is produced. So at very high energies, we have here kind of absorption effects. So the very high energies gamma rays get absorbed by pair production, whereas here you don't have the starlight, which is responsible for this absorption effects. Yeah, so this is one thing we do with binaries. So we have to fold the data to see that modulation. And the very important thing is actually to detect the periodicity. This we do with, well, with these kind of power spectra. So we make a scan of possible frequencies, and if there is kind of a periodicity, we see peaks. Well, if we have a significant peak, we can be sure, there is a frequency we detect, so this must be kind of a periodicity that we have found. So for this source, we see the frequency exactly at 3.9 days, and this we detect at high energy, at very high energy, at X-rays, in the optical. So for this source, we have not only at high and very high energy data, but also at the X-ray and in the MEV range. And here the different colors, they represent inferior and superior conjunction. So it is very difficult to model these kind of binary systems because they have a lot of, well, they show a lot of features. So you cannot just make an extrapolation, for example, from MEV to GeV. But what can we say about this source? That is it shows a stable behavior at inferior and superior conjunction, which makes it a good source for doing binary studies. Yeah. So what is the nature of this source? There are hints that it is a pulsar with a massive star. So why? If we have a look at the spectrum, so we have here the GeV data, here the very high energy data, and we know from the Fermi data we have a lot of pulsars. We detect more than 100 pulsars in our data sets, and they all show a spectrum shape like this. So pulsar-like, this is one hint why it can be that in LS5039 we have actually a pulsar as a compact object. And this bump here, it is very typical for pulsar wind nebulae that we also detect a lot with, especially with Hess, which have a good view to the galaxy, to the galactic plane. So the spectral shape of this source says that it may be a pulsar, it may has a pulsar with a compact object as a compact object. Yeah, I mean we did a lot of searches for pulsation in the X-ray, in the radio, but pulsation was not detected up to now. Okay, another source that we detected at high and very high energies is 1FGL J1018. This is a very interesting source in the sense that normally binaries we first detect in radio, we first detect in X-rays, but this is the first source that we first detected at GeV. And then following, we searched in X-ray and in radio and then in VHE, and this binary could be confirmed. So how was this done? As I said, when we look for frequencies, we are using these power spectra, well, special algorithms. So we have a catalog of sources at GeVs. So this was the first catalog after the launch of the Fermi satellite, this 1FGL. So we took all these 1FGL sources and made a scan of frequency. And there was one source where we actually found a periodicity at 16.6 days, so this is this peak. Yeah, and then afterwards we looked at other wavebands where we could find then the periodicity. So this is a quite nice finding that was done. So afterwards we looked at the VHE data. So we took the data, folded them with a periodicity of 16.6 days. This is shown here, the flux again over the orbital phase. When we always show two orbits just to see this nice modulation. Here are again the GeV data, and here are the X-ray data. So the difference to the source I presented you before is that here the VHE and the GeV data are actually in phase and not in anti-phase like in the source before. Yeah, for this source actually the orbital parameters are not very well defined, so we cannot make a lot of conclusions about the relation between the compact object and the massive star. Yeah, also, as I said, there are a lot of differences to LS5039. There are also a lot of similarities. So if we look at the spectrum, so here we have, in blue are the points of LS5039, and in black the points of J1018. So in the GeV they are really, really similar. Well, and in TeV, okay, we cannot separate them between inferior and superior conjunction, but here the similarity is very, very strong. So it seems that there is, at least at GeV, the nature of the emissions is kind of similar. So as I said, the interesting point of this source is that it's the first one that we really detected just through GeV observations. So as I said, we have the gamma ray binaries and we have the microquasars, and one example is this Cygnus X-3. Again, it is in a very complicated region, so this is a GeV count map. So here is a source of interest, and there is a lot of stuff around, which, as I said, you have to subtract. And about the source, well, it is a high mass X-ray binary. The companion star is a Wolf-Rayet star. And there we are pretty sure that the compact object is a black hole, which is emitting relativistic jets. And this source shows a lot of radio outbursts. So there are peaks in the radio flux. Yeah, it has a very short period, just of 4.8 hours. And the interesting thing is we don't see this period always. So if we take all the data in the GeV and we look for periodicity, here's again this power spectrum, we don't see any peak in the frequency. But if we look at time windows where we have a flare in the radio, during active periods, you see that we have a peak here at the frequency of, well, with a period of 4.8 hours. So this we can only detect if the source is in an active state. Interestingly, this source could not be... I will come to it. Yeah, we don't detect it at very high energies. We made a huge campaign, and still doing with MAGIC, but it is not detected yet. Yeah, and now to your question. Well, there was a very huge flare in the radio in 2011. And nicely, we have a lot of data. We have data in the hard X-ray, which are here the green points, in the soft X-ray, in the GeV, and in the radio. By the way, here X is the time, and on the y-axis are the corresponding fluxes. So, and it seems that to see something in the GeV, there are three conditions that have to be fulfilled. You need a high level of soft X-ray, a low level of hard X-ray, and you need variability in the radio flux. This is what we see here. So here's in blue is the detection in GeV. So when we could detect the source, all these arrows are upper limits. Well, when this hard X-ray is going to a lower level, this is going to a higher level, and when we have a lot of variability in the radio, and here it is going up, this is when we have the detection at GeV. And all these different energy ranges, they point to different locations in the system. So the hard X-ray, they are pointing to the corona. So you have your black hole. Around the black hole, you have the corona and the accretion disk, and then perpendicular to it, you have jets which are emitted by the black hole. So the hard and the soft X-rays are then pointing to the corona, to the disk, and in GeV and in the radio, this is the non-thermal emission pointing to the jets. So and since we have this connection between the radio and the GeV, it seems that the emission of the GeV is happening inside the jets and not close to the black hole. So here the nice thing is that we have really a huge picture of the source to different locations, and it's kind of a small AGN, a small active galactic nuclei that normally we find outside of our galaxy. Okay, so coming back to the gamma ray binaries, a very interesting one is PSR B1259. Here you see a sketch of it. So this is the neutron star, this is the BE star, and it is surrounded by a decretion disk. So for this source, we are sure that here this compact object is a neutron. It's a pulsar because we see the pulsation in the radio. Yeah, it is a pulsar with a period of 47 milliseconds, and the whole orbital system, it has a period of 3.4 years, so quite large. It is quite elliptic. Yeah, and here the peculiarity, the interesting thing. So here we have again the time, we have here the fluxes, and this dashed line is the periastron. So this is the passage when both objects are closest to each other. And what we expected actually was to see a maximum at this point and at this point, so when the neutron star is passing the disk. But this is not what we saw. So let's focus on this panel here. This is the Fermi light curve, the GeV light curve. So before periastron, we don't detect the source. We detect the source, but this high flux actually happens after it passed the disk. So this is something the theorists have kind of trouble to detect it, to model it. Here on top we have the very high energy light curve, and also at very high energies, this is the only time around periastron when we can detect the source. Okay, here we have the X-ray, where we have actually two peaks corresponding to the passage through the disk. Okay, and this is the radio light curve. So to get a better idea of the system, so I have a very small movie to entertain you. Where is my mouse? Okay. So yeah, this is the neutron star orbiting the BE star. So at this part of the orbit, we can detect the pulsation of the pulsar in the radio, but we cannot detect GeV nor very high energies. This we can detect just in this part, but we cannot detect the pulsation of the radio, also because of absorption effect, because of free absorption here. But here we can detect GeV and very high energies. Yeah, so we had, it has a very long orbit, as I said, 3.4 years. So of course we want to look every 3.4 years what is happening. So the last time it was in 2011, no, the time before the last time. And then in 2014 we were all very exciting what will happen. So various instruments had a look, Fermi of course too. Yeah, and here are the corresponding light curves. So again, this is the time, this is the periastron passage. In blue are the old data from 2010, and in red the 2014 data. And you see, again here we detect the source, but just after the neutron star passed the disk. It seems quite similar, but there are small differences. There is the flux evolution is quite different between the red and the blue points. And the peak of the flare was 2 days delayed with respect to the 2010 flare. Now people are trying to explain this. This can be, well, as I said, around the BE star we have this decretion disk, and of course this disk is not very homogeneous, so maybe because of inhomogeneities in the shape and the density of this disk, there can be differences between the different passages. Okay, so the most important point of this source at the moment is, yeah, here we know what is the compact object. It is a pulsar. Yeah, and we are trying to understand still the emission at GeV and very high energies. Okay, this source I want to present just very, very shortly has J0632. It was actually detected by chance by the Hadasch experiment. It has also a quite large orbit of 320 days. Here you see the folded light curve, the flux, here again the phase. So the gray points are the X-ray data, these colored points are the VHE data, and they are very nice in phase. So we have a peak here, we have a small dip here, and up to now the data can be explained very nicely by a one-zone leptonic model. So that means if you look at the spectrum, so the flux over, well, here's the frequency, here are the spectra in the X-ray, the spectra in the very high energy, and these spectra can be modeled by a simple one-zone model that means that in the X-ray is produced by synchrotron mechanism, and the very high energy emission by inverse Compton. Interestingly, this source here in the GeV range could not be detected by Fermi. This is the only binary which we detect at very high energies, but not at high energies. And this is still a mysterium why we don't see it. But we are still observing it with our different campaigns. So with MAGIC, with Veritas, and the newest data that we have, they confirm this shape in the light curve that we are seeing. Okay, now my favorite source is the one that Marina already introduced. It's LSI 61303. Here is a small sketch. Again, here's the BE star orbited by the neutron star, and we have the periastron passage here, upastron passage here. I will talk about these passages a lot, so remember the colors and the names. Okay, this source had quite a history. It was discovered in '77 by the satellite COSB, then in TeV energies by MAGIC in 2006, in GeV with the Fermi satellite in 2009, and in both energy ranges we could find the periodicity of 26.5 days. Yeah, as I said, it consists of a compact object, which we don't know. It's a neutron star, a black hole, and a BE star. And I want to stress here that, well, BE stars, they know that they lose mass in a circumstellar disk, which is quite important for this source. Yeah, very interesting is here we don't have just an orbital period because of the neutron star orbiting or the compact object orbiting the BE star. We see there also a superorbital periodicity of 1,667 days, which is not clear yet why we see this periodicity. So this periodicity, well, since it's quite long, it's more than 4 years, we need quite a huge data set to detect it. So it was first detected in radio. We have more than 20 years of radio observations of this source. And there is where it was detected first by Samanov and Gregory et al. 2000. So here is the corresponding folded light curve. This is the, well, let's say the radio flux over phase. And you see nicely the modulation of the flux. And this was not only seen in radio, but also in the H-alpha line. This is the equivalent width of the H-alpha line. It shows also kind of a periodicity. And already there, people were thinking, maybe this periodicity or superorbital periodicity is somehow linked to the disk we see around the BE star. Because it is known that these disks show a quasi-cyclic variation. We know it also from isolated BE stars. So this is radio. Now we have more instruments, X-rays, and so on. So what we did, we started a campaign in the X-ray with the RXTE satellite from 2007 to 2011. So almost one super orbit. So we had a huge data set. What we did, we took the data set and cutted it in half-year bins. So what you see here is the folded light curves for half a year. So here we have the counts, here we have the phase, and we see that they are not equal. So we have sometimes the peak is here, sometimes the peak is here, sometimes we don't see any periodicity at all. So we were wondering, okay, why is it? Is it somehow connected to the superorbital variability? So what we did, we calculated the average flux of each of these phasograms and plotted it over time. So these red points, this doesn't show the average flux, it shows the peak flux of each of these folded light curves. And this peak flux, we plotted then over time. These are the red points. Yeah, and we see that there is a variation for sure. This dotted line is the superorbital periodicity we know from the radio. So what we did to our data, we fitted them with the same period. Well, there is a nice fit, but as I said, this is just one superorbit. So the only conclusion we can draw up to now is that there is a variability, but we cannot really say for sure that it's sinusoidal, although this fit looks very nice, right? So in X-ray, we see a variability. How does the things look like in GeV? So in GeV, we have this very nice instrument. This is the Fermi satellite. On top of it, we have the Large Area Telescope, which is sensitive to gamma rays between 100 MeV and 300 GeV. So here what we did, we had 5 years of data, and we did the same. We took the whole data set, cut it in half-year bins. So here each of these panels, again, represents half a year of data. On the y-axis, the flux. On the x-axis, the orbital phase. And the different colors represent the green one, the periastron passage, when the objects are closest to each other, and in red, the apastron passage. Okay, here we see a trend, kind of a maximum around periastron and a minimum around apastron. But again, they don't look the same. They show kind of a variation. And this you see nicely if you make an overplot of all these panels, which I did here. So here they are all overplotted, and if you look at just one phase bin, for example here, you see that there is a huge variation in the flux. They are following the same trend, but anyway, in the orbital, the phase bins, we see a variation. So again here, it can be that it is correlated to the superorbital variation. So what we did here we calculated the average flux for each of the panels I showed you. So we have the flux over time, and here you see already by eye, and if you fit a constant line, it is clear that we see a modulation. So the question if there is variability in the superorbit, we can clearly say yes, there is a variation in the superorbit. So these are 5 years of data. Now we have much more. We have almost 8. And I can tell you that this trend is going on. So with more data, now it is going up and then going down again. So the thing looks pretty similar like in the radio up to now. So, but we had a little bit closer look to this data set. What we did now, I folded these phase bins into the superorbit now. So what I did, each of this phase bin, for example, 0 from 0.1 of each of these half-year panels, I folded into the superorbit. And this I did with the next phase bin and with the next phase bin. And the result is this one. So now each of these panels, they represent certain orbital phases. So the first panel represents the orbital phase from 0 to 0.1, the second one from 0.1 from 0 to 0.2, and so on. So again, here in green periastron, in red the apastron passage. And if we have a closer look to these light curves, so if we just look at the periastron passage and we do a fit with a sinusoidal or with this constant line, we can say that here we have kind of a constant behavior. We don't see a variation. So we can say that here the conditions for the generation of GeV emission does not change significantly. If we now look at the apastron passage, there we see a nice modulation of the flux. So here something must be going on in the production of the GeV emission. So and here we come again to the idea what people had at the beginning, that this variation we see is connected to the variability of the circumstellar disk of the BE star. So also here that you have an idea of the system. This looks like this. So you have the BE star here in bluish, the disk, and the compact object is orbiting the BE star. It is sometimes outside the disk and it is sometimes inside the disk. So we have the period, and then we have this difficulty that we also have this disk there. So the system is quite complicated. But yeah, one idea is that the superorbital variability is connected to the disk. Here I have a very simple sketch of the idea people are having. So here again is the orbit, so the BE star orbited by the compact object in black, and here in pink and in blue this represents the disk. So here we have a relative small disk, here we have a relative large disk, and if we look at periastron, there the compact object is always affected by the disk, it is always inside. When it is at apastron, it is in periods of a smaller disk, it is outside the disk. When we have a large disk, it is inside. So we are swapping between these scenarios. So at Apastron, this is where something should go on, and this is what we see in our data. So one thing that is known is that the stellar disk can be traced or is connected to the H-alpha line. So it is known that the H-alpha line is grown larger that the disk is grown larger when the H-alpha line is going broader. So we had to look at all the H-alpha data that we could find in literature, so from 94 to 2015. And what we did with them, we folded the equivalent width into the superorbital period, so into this 4 years. So these are all the data we have. It is quite a mess if you look at them, and you see they have a quite large variability. So we have even a variability during one night. So it is very difficult to say something if we see a modulation or not. So we binned the data into a superorbital phase bin of 0.05, and here we can see and we can say that, yeah, there is a modulation in the H-alpha. And if we have a maximum here, so that means we have a larger disk with a high mass loss. At the minimum, we have a smaller disk with a low mass loss. So if we have it in H-alpha, we have it in GeV, what is happening at very high energies? Also here we conducted a large campaign together with MAGIC and Veritas, where we observed the source almost 1 decade. But yeah, as you know, it is quite difficult to observe with Cherenkov telescope. You have the sun, you have the moon, you cannot observe all the time. But anyway, if we take all the data we have and we fold them, so we have the flux over the superorbital phase. Also here we see, at least we have kind of a high state and kind of a low state. We did also a fit with a sinusoidal, but again, we cannot say that these points are following a sinusoidal, but we can say that yes, we see a variability along the superorbit. So if there is a variability in all these different energy ranges, there must be a connection, or we think there must be a connection. So we looked for a correlation between the H-alpha emission and the TeV data. Unfortunately, we could not find any correlation, so we have here on the y-axis parameters of the H-alpha line. Here's the equivalent width, the full width half maximum, and the velocity. Here we have the TeV flux. Yeah, but here we did not find any significant correlation. This does not mean that this correlation is not there. It can be that it's simply blurred because the H-alpha is quite variable, as I told you before. So we are still working on it, and let's see what we will see in the future. So summarizing the sources I presented, I summarized them here in this table. Here are the different sources with their different parameters. So normally, or for most of them, we detect them in the GeV and the TeV range, all but these source, Hadasch J0632 and Cygnus X-3. And actually, I have to update this table because this source, Cygnus X1, was recently detected also with Fermi. So you see that the small family of gamma ray binaries is kind of growing. And now recently a new gamma ray binary was detected, so 2 months ago, in the Large Magellanic Cloud, so outside of our galaxy. This was quite a surprise because, well, in our galaxy I presented now 5 sources, so we expected that we will find more in our galaxy. But the next one we found is actually outside of our galaxy, so you see here the nicely modulation in the phasogram. So this is the brightness, this is the phase. And this source was found with the same technique like J1018. So we took the newest catalog of the Fermi data. This is the 3 FGL. These are 4 years of data, 4 or 5 years of data. And we made a frequency scan of all of them. And there we found this one source which has a peak at this period at 10.3 days. So again, here we had then also a look at other wavelengths. So this source is actually located in this supernova remnant. It has also a massive star as a counterpart. And then looking into other wavelengths, we found that it is consistent with X-ray and radio point source. Here you see a picture in the optical of the region. So here is the binary actually. And this is the whole, well, this is zoomed into the Large Magellanic Cloud. And then if we compare all the different wavelengths we have, so we have here gamma, we have X-ray and radio, and also here in different wavelengths we find a variation, so it points to a new gamma ray binary. And the last, well, where we can really confirm that this is gamma ray binary is looking at the radial velocity, which you see here. These are the black points, the radial velocity over phase. Yeah, and you see this modulation. So we can say, okay, we discovered a new gamma ray binary. It is thought that it is a neutron star, but we cannot rule out that it is a black hole because we don't know what is the inclination of the system. Yeah, and this finding is a little bit, well, it is very interesting. So first, it is the second gamma ray binary discovered by the Fermilab. It is actually the most luminous gamma ray binary we detected ever. Yeah, and as I said, we expected much more gamma ray binaries within our galaxy. There are some studies. We expected more than 30. We have 5 up to now. And now the next one we found outside of our galaxy. So maybe this estimation is wrong. Have we detected all of the gamma ray binaries in our galaxy? Is this because of our instruments? Or do we see gamma ray binaries only if they have a very fast rotator, so if the neutron star is spinning very fast? So this one, for example, has 19 milliseconds at birth when it is born, this neutron star. So this finding is very nice, very interesting, and now opened kind of a new window what to think about the whole family of gamma ray binaries, if we will find more or not. So studies are ongoing, and yeah, thank you for your attention.
Thank you so much, Daniela, for your talk. And I just want to, before the question, point out that for instruments like MAGIC, maybe for Fermi is more easy, but for MAGIC it's very complicated to see such objects like that, you know. So for us it's very important to study binaries because, as you know, Cherenkov telescopes are not like the normal telescopes, and for them it's very complicated to understand what's going on in the source we are observing, especially when, like in binary systems, the objects and the fluxes you are measuring are so close to each other. We don't have a great resolution in distinguish the distance and the morphology of the sources like a radio telescope could have. So it was very nice to hear about that. So let's go on with the questions.
Daniela, that last source you're talking about, it's something else about it that makes it very interesting compared to the others. It's a very early type star, the companion that you're dealing with there. The implication is it's a very massive star. So the evolution of the system, I think, is going to prove to be very interesting. But my main comment, which is going to be about the superorbital period, just to say that in fact, one of my students, Andrei Radulemanana, did a survey of all the optical X-ray pulsars in the SMC, and we published that about 4 years ago, and every single one of them shows superorbital periods in the optical using the OGLE data. So and you see the modulations. These are not tiny. Some of them are huge, you know, a magnitude or more, which in a given that they're all BE X-ray pulsars, that means you're seeing massive changes in what you call in the decretion disk, the excretion disk, if you like, that the rapidly spinning B star is throwing out. And so that kind of behavior is certainly to be expected. But what was interesting is that the period you get is quite a bit more than we would have guessed, because we've got quite a nice relationship between the orbital and superorbital periods. But this one is quite a bit longer, and I thought that was very interesting.
What are the periods you detect, or the super periods?
Well, they all come out with the OGLE data, and the periods, the ratio is more like 10 to 20 than the 80 you're getting there.
Okay, I didn't know. I will have a look. That's interesting.
Take a look at our paper.
Thank you.
Right, we can check that afterwards.
Well, I have the paper here. We can have a look then.
Right.
Questions? Well, okay, I know it was a very exhaustive talk, and she covered a lot of, she covered a huge amount of things about the binary you studied in very high energy and gamma, of course, high energy. Well, I have a very simple question for you. As a lot of magicians, people working with magic, you are also involved in this fantastic, huge project. There is the Cherenkov telescope array that will come in La Palma, so we are talking about a lot of Cherenkov telescopes like magic. And I imagine that with the Cherenkov telescope array, it will be possible to have an improvement, a considerable improvement in the study of these objects. So what are your how can I say, predictions about this?
Well, one of the things what we want to see now, if we can really detect, if we detect more gamma ray binaries or not, or if it's really, the evolutionary stage of gamma ray binaries is quite short. So just a short time of their life, they are a gamma ray binary. So this can be one of the reasons why we don't detect so many. But with CTA, we have much better sensitivity, so I don't know. We will see if we detect more or not. And we can go lower in energies. So we hope to close the gap between the GeV and the very high energy ranges. So we have the nice Fermi spectra, we have nice spectra from MAGIC, HESS, or whatever. But there in the middle, sometimes we are missing points. So maybe there we can make nicer modeling and we get an idea what is the nature of the compact objects then. So it's the better sensitivity and also the lower energy threshold where we hope to gain a lot. But I think for these systems it's very important to have this multi-frequency picture. It's maybe valid for all the sources, but yeah, especially for these.
But these sources you were talking about are all relatively close to us, right? Only one is in another galaxy.
Exactly,
right?
they're all close to us. This new one is in the Large Magellanic Cloud. It is really the brightest that we ever detected. But even this one, if it would be a little bit farther, we would not be able to detect it. So we are really limited to our field of view, kind of, or with our sensitivity to detect binaries farther away with these luminosities. So
CDA will increase also the possibility to go farther away and find the other binary system more far away than our galaxy.
Should be, but okay, up to now we never found a binary just from the very high energy. So the highest one was at GeVs, right? But yeah, let's see.
But given that point, don't forget the LMC only contains 1% of the mass of the Milky Way. So isn't it rather odd that the most powerful gamma ray binary is not in the Milky Way? Just think how bright the source would be in the Milky Way.
That's true. Yeah, it's
True, that's telling you what you need, the conditions to make it.
Okay, if there are no other questions, yeah, let's thank Daniela again for this wonderful talk.